All right, let's start our lecture today. Good afternoon, everybody. So now today we will start a new chapter on momentum and collision. Now, I think momentum you have learned on momentum already in high school, but we will extend our discussion to some more difficult two-body upright collision. And also we will discuss about the idea of center of mass and how to express Newton's second law for a system of particles in terms of the center of mass. Instead of just expressing Newton's second law as for a single particle, we now extend our discussion for a system of particle extended as an extended body, or so we can be able to write down Newton's second law in terms of the acceleration, not for a single particle, but the acceleration of the center of mass of a system of particle. So we are going to do that in this chapter. Now, let us have a brief review of the idea of momentum for a single particle. Newton's second law is written as the net force F equal to the mass multiplied by the acceleration, dv dt. And since the mass m is a constant, we can move the m inside the derivative, and we call the combination mv as the linear momentum of the particle. That is Newton's second law written in terms of momentum. So the momentum P is defined as the mass times the acceleration mv. Okay, we usually simply call this momentum, but in a university study, we have to distinguish between linear momentum that you learn in high school and also the angular momentum, the rotational counterparts of the momentum. So here we emphasize that the momentum here we define is for linear case. That is for for the linear motion, but not for the rotation. Now, so Newton's second law can be written as at the following form: the net force F is equal to the rate of change of the momentum dp dt. And so that means if there's no net force, then the dp dt will be 0, and that means p is a constant. There is no the momentum is conserved. But that is for a single particle only. What makes momentum important is not for a single particle, but for a system of interacting particles. When the particle interact with each other, we find that as long as the system is closed, as long as there is no external net force acting on the system, the total momentum of the system will be conserved. Not for a single particle, but the momentum for the whole system will be conserved. So when the particle interact with each other, one particle may transfer the momentum to another particle, but the total momentum remains constant. That is the important law in physics that we are going to discuss in this chapter. Now, so we can easily make a generalization to 3 dimensions. We simply replace the scalar value with the vector. Okay, dv vector dt is equal to the net force F. And momentum has a dimension of mass multiplied by the dimension of velocity, and that gives me a dimension of mLt minus 1. And the SI unit is kilogram meter per second. The mass is kilogram, and the velocity, the dimension unit of the velocity is meter per second. So momentum has a unit of kilogram meter per second in SI unit. Now we discuss a system of particle. To make things simpler, we start our discussion with 2 interacting body. Okay, we will let you see why we can define the momentum, why the system momentum is so important in this case. So we consider 2 body, 2 block. They are touching each other, M1, M2, and they are at rest on a frictionless table. And M1 is acted by an external force. We call it F. Okay. So there is an external force acting on M1, and of course M1 exerts another force on M2. Okay, so we draw the free-body diagram for M1 and M2 respectively. For M1, there are two forces acting on it. One is the horizontal net external force. The other force is from M2, okay? Because M1 and M2 are touching, and so they exert a action and reaction pair on each other. And that force I call it R, okay? And of course, for the mass M2, there's also an action force acting on it, and that is again R. These two forces are an action and reaction pair. They act on different body. They are M1 and M2 respectively, and they are in opposite direction. They are equal in magnitude and in opposite direction, so they form an action and reaction pair. Now, so we write down the equation of motion for M1. The net force is F minus R because they are in opposite directions, so there's a minus sign here. And the net force is equal to dp1 dt. Okay. For the mass M2, we only have one force. So the net force R is R, and that's equal to dp2 dt. Now we add the two equations together. When we add the two equations together, the internal force cancel. Because the internal force are a pair of action and reaction, they are equal and opposite. And they appear with opposite sign in the two equations of motions of the two bodies. So when you add up the equation of motion of the two bodies, they cancel. Okay, because for this one you have negative R, and for the other equation you have positive R. So when you add them up, you cancel the R. And so that's why the internal force doesn't matter. Okay, it does not appear when you add up the two equations. If you consider the system as a whole, then it will tell you that the final equation is that the net force is equal to the dt, the rate of change of P1 plus P2. And P1 plus P2 is the total momentum of the system. Okay, so now the internal force has gone because they are opposite and they cancel in the equation. And so you got an equation that relates the external force acting on the system to with the total momentum of the system. That is the total momentum back P is equal to P1 plus P2. Okay, so that is a nice thing because you don't have to consider internal force. Okay. Now, so P is defined as summation PI. Now, although we only, for simplicity, we only consider two interacting mass. In fact, the formalism can be easily generalized to many interacting body. Okay, and by that same token, the internal force will also cancel, and you will arrive at the same equation. The external force being equal to the rate of change of the total momentum of the system, not just a individual body, but the sum of all the momentum of the interacting particles. Okay, so Newton's second law for system of particles says that the rate of change of the total momentum of a system is equal to the net external force acting on it. So that is the answer. That is what we want. And in symbol, we write F as dp dt. You can write a symbol, a vector also. If you add a vector sign, then F vector is equal to d back P dt. The back P is not a single particle momentum. The back P stands for the momentum, the sum of the momentum of all the particles in the system. Okay, is that clear? Now, so the internal force cancelled by Newton's third law. So no matter how complicated they are, so we don't care about them. So when the external force is zero, when the net external force is zero, dp dt will then be zero. And so that is the total momentum conserved. Okay, the total momentum become a constant. But the total momentum is a sum of individual momentum, of the particles. So the total momentum being conserved, it means that during the collision during the interaction between individual particles, there might be an interchange of momentum from one particle to another. If two particles collide, one particle may lose momentum, the other particle may gain momentum. But since the lose and the gain are the same, right, of the same magnitude, but of equal sign, opposite sign, so the total momentum still remain constant if you calculate the total momentum One increase, one decrease, and so you got the total momentum unchanged. And that is the law of conservation of momentum. If the external force, in the absent external force, or if the net external force acting on the system is zero, the total momentum of the system is conserved. Okay, so these are the physical idea. These are the physical idea for the conservation of momentum. Now, I think you understand this idea. But now we would like to generalize our discussion to more formalistic way. So we will formulate it using more sophisticated mathematics. Okay, the ideas are there. Okay. Now somebody asked me a philosophical question. Why I say that is a philosophical question? Because somebody asked me, what is the nature of momentum? I would not be able to answer the nature of momentum. Just like you asked me a question. What is the nature of electric charge? I cannot answer you. I only can tell you how the momentum appears in the equation and how this is reflected in daily phenomena. For momentum, you know, that is an important quantity in collision. For example, if a body with a larger mass, it collides with you, okay, you will be hurt more because the body has a large momentum. If the body has a large velocity, it carries a large momentum, and so it also produces a larger collision effect on your body. Okay, when a trunk which has a large mass will collide with a small car, the trunk has a large momentum, so it will damage the small car a lot. And if another car have a high velocity, even though it does not have a large mass, it have high velocity, it carries large momentum. So when it collides with another car, it also causes a lot of damage. So the momentum actually measure the amount of collision how to say that. If you have more momentum, then you probably will be causing more damage when you're colliding with other bodies. Okay, so that is about the idea. Okay. Now, so let's make it more formal. Now, I want to make the mathematics more formal, just to let you get familiar with the use of mathematics in physics. Okay, this is important if you are going to study some higher level course in physics. Okay, in those courses, the mathematical language will become very formal, and so you have to get use of understanding what is happening in those mathematics and what's the meaning of that. Okay, so now we consider n particle, and we label them as M1, M2, the mass of them as M1, M2, M3, up to Mn. Okay, and so we now consider a pair, Mi and Mj. I and J are two arbitrary particles. We consider interaction between the particle Mi and Mj. Now, let's consider Mi first. Mi, this particle, may be acted by an external force, right? And the external force acting on the I particle, we call it MIE. Now, the superscript E here is not the power. It is only a symbol. The symbol denotes that the force is an external force. It is not due to the collision between the particle. It is due to the external agent. For example, my hand pushing the particle Mi, and so there's an external force. Is that okay? So you have external force, but you also have internal force due to the interaction between these two pairs, right? The external force acting, or the internal force acting on the particle Mi due to particle J, I call it Mij. Now, Mij is easy to memorize, although you have two index here, which sounds rather complicated. But as long as you remember the order of these two index and the meaning, it will not be difficult to understand what this term means. Fij is in fact the force acting on particle I. The first index specifies the particle that is being acted by the force. And the second index, J, it specifies the particle that produces the force. So Mij, Fij, is the force acting on particle I due to particle J. Is that okay? The force acting on particle I, but that force is coming from particle J. Okay. Now, but we have an action and reaction pair, right? If J acts a force on Mi, then I also acts another force on J, right? And the force, the reaction force, is denoted by Fji. Right? The particle acting on J due to particle I. So Fij and Fji, they form an action reaction pair. Is that clear? Now, so if I ask, what is the total force acting on particle I? The total force may include the external force, that is Fie, and it also must include all the internal force acting on particle I. So we have Fij, but J can be any other particle, right? So I have to form a sum. Because for the particle I, there may be many other particles acting active force on him, right? So I have to sum over J. J is a sum from 1 to n, okay? There may be many other particles have a force acting on him. So I have to form a sum over all these other particles. And by definition, we can make Fii equal to 0 because the particle I will not exert a force on itself. Okay, it's the other particle that exert the force on him. Okay, so I form a sum of Fij over J from 1 to n. Okay, and the total force, this is the total force. And of course, by Newton's second law, this is equal to the change in momentum of particle I, dpi dt. Is it okay for you? The language is a little bit formal, but if you understand the index very carefully, you understand the meaning, then there's not difficult for you to write down this equation. Okay. Now this equation is for particle I only, but the particle I is general. I can be particle 1, I can be particle 2, I can be particle 3, and I can be particle n, right? So you can use the value of I to specify different particle, the equation for different particle. So we have n equation. For equation for I equal to 1, you have the force acting on particle 1. For I equal to 2, you have the force acting on particle 2. That is the equation of motion for particle 2, and so on and so forth. So you have n equation. They are the equation of motion for each of the particle. Okay. Now, so we add up this n equation. We form a sum over I. I is from 1 to n. The rest summation is that we sum up all the equation of motion for the n particle. Okay. Now, so we form a sum on both sides over I, but it's not over J now. It's over I. Okay. Now, if Fie is the external force acting on particle I, and I sum over I, that means I sum over all the external force acting on the particle. And that is a total external force that becomes a total external force F. And also on the right-hand side, if Pi specifies the momentum of the I particle, and now I sum up all the particle, then summation Pi is a total momentum of the system, which I denote by big P. Okay. Now the tricky point is this double summation. I sum over I and J, Fij. Okay. Now imagine I and J runs over all the possible value from 1 to n. And that means in the summation, for example, I consider the pair. I may consider the pair like this. I may consider the pair I equal to 1 and J equal to 2. For example, I consider this pair. Okay. So there is a term here, if I and j 1 over 1 to n, there is a term that with I equal to 1 and j equal to 2. So I have the force F12. Is that right? But I can also have another term because I and j runs over all the numbers. So I should have another term with I equal to 2 and j equal to 1. And that's give me F21. Is that right? Now, you can see when the two terms added together in a pair, because these two forces are action and reaction pair, so they are equal in magnitude and opposite in direction. So they cancel, right? And so the internal force, they cancel in pair. Fij always cancel with Fji. And so the sum of these two terms is always 0. And so that means when I sum over all the interactions, internal interaction, the internal force always cancel by Newton's third law. And so the double summation just give me 0. And so eventually I would have Newton's second law for a system of particle. The total net force acting on the system being equal to the rate of change of the total momentum of the system. Okay, so that is the formal way to derive the equation. Okay. Now let's say a little bit about collision. What is so special about collision? Why do we distinguish collision with all other interaction? Now, when you learn Newton's second law for the first time, you may have learned the nature of force, right? You may have learned contact force, right? When you push an object or pull an object, the high school physics teachers tells you that when you push an object and pull an object, that is a contact force, right? But that is not to be that may not be a collision force. So what is so special about collision force? Why do we have to specify some kind of force known as a collision force? Now, collision refer to a contact force. I think mostly contact force refer to a contact force which has a very short duration. So when two bodies collide, the collision happens in a very short time. So that makes collision different from other interaction. If you push or pull an object, you probably apply a gentle force to that object for quite a long time. But for collision, the two bodies just touch each other at a very brief moment. Typically, that lasts for example, if you have two balls colliding with each other, the collision time may be of a thousandth of a second, or several thousand of a second. Okay, it's of the order of 10 to the power minus 3. Even for collision of two cars, for example, the collision time may be 100th of a second or 10th of a second, which is again very short, considering the large body. The collision may happen in a fraction of a second, or even 100th of a second if the collision time is if the speed is large. Okay. So there are many different kinds of collision, like for example, even water colliding with the surface, water surface, a collision, a golf ball, a golf cup colliding with a golf ball, or even the moon colliding, Earth colliding with another planet 4 billion years ago. That is a collision. Okay. And of course, this collision have different time scale, but the nature of the collision is that they are relatively short. And in a relatively short period of time, the change in momentum is very large. And that means the collision force at that very brief moment is actually very large. And that collision force dominates over other forces. Okay, when you have two bodies colliding, at that time of collision, the force is so large, okay, it dominates all other forces acting on the two bodies. For example, it dominates over gravity. In a very brief moment of, say, 1,000th of a second, the collision force is so large, it's much larger than the force of gravity. It's much larger than the own weight. So within the collision time, all the other forces could be neglected. You only concentrated at a very large collision force. That is a property of collision. Now, when we discuss about collision, we may like to rearrange Newton's second law in this form. Instead of writing F equal to dp dt, we can move the differential dt to the right-hand side. So dp is equal to f dt. So a small change in momentum is brought about by a force, the collision force applying on the object for a very short time. Okay. Now we integrate over the collision time interval. For example, if the collision starts from time ti and ends at time tf, we can integrate over the times on both sides. And so the right-hand side will consist of an integral of f over the time t from ti to tf. And the left-hand side, before the collision, now the left-hand side will give a change in p. But what is the change? If the initial momentum of the particle is pi and its final momentum is pf, okay, there's a change in momentum in that of that particle. So initial momentum before the collision is pi and final momentum of the particle is pf. So the change in momentum is pf minus pi. Okay, so we arrive in a very important equation. The change in momentum of a particle, of a body during collision is equal to the time integral of the collision force over the collision period. That is the important equation that you should know. Now this quantity, which consists of the integration, the time integration of the collision force, is formally known as the impulse. Now in discussing about work and energy, we have introduced the integral of force. But that integral of force is integrating the force over the displacement. It's f dx, right? The x is the displacement. And we found that the f dx integral gives you the work done by the particle. That's the energy transfer to the particle or taken away from the particle. So that corresponds to the energy. But now we have another integral. That another integral is not with respect to distance, with respect to displacement, but with respect to time. If the force is integrated with respect to time, that gives you an impulse. And the impulse is equal to the change in momentum of the body. Okay, so we denote this integral by J, and J, the impulse, is equal to the change in momentum of the body. Okay, now if I plot the graph of F versus time, the force versus time, the collision force in the intermediate steps might be very complicated. You imagine now the when two body collide, it happens in a very short time. But during that short time, the variation of force is still very complicated. The force will rise from 0 to a very large value, right? During that collision, the force will rise to a very large value. And when the body separates, it suddenly drop again. That variation is very complicated. And we probably will not know, will not be able to measure how the force exactly varies with time. We do not know, right? We simply, the force is, most often the force is too short to be, the variation is forces in, the variation of force is too short to be measured precisely. So we do not know the detailed variation in most of the cases. But from the change in momentum, we know the force integrate over the time is equal to the change in momentum. We know the final and the initial momentum, we know the impulse. Okay, so that is the idea. Why we use the idea of impulse to discuss about the collision event. Now there's also another concept known as average force. Now we have the collision starting time at Ti and collision ending time at Tf. The force variation will be very complicated, but let us take an average. How do we take an average? We imagine the time interval being the same. But now we imagine there's an average force. The average force acting on the particle. The average force is constant over the whole time interval. And how do we measure that FH force? Well, the FH force should produce the same impulse as the real force. Okay, so if when we draw a graph of F versus T, the integral of F over T is the area enclosed by the curve. Is that right? And so we can draw a FH force. The FH force encloses an area which is equal to the FH force multiplied by the time interval delta T. And I can choose the FH force in such a way that the area enclosed by this rectangle is the same as the area enclosed by the true force. That is the integral of F. Okay, so that means I can define the FH force by this equation. The time integral of F for the real force is equal to the FH force multiplied by delta T. Okay, so I can also move delta T to the right hand side if you like. Now, so I can write out this equation. The change in momentum Pf minus Pi is equal to the impulse, which is the integral of the true force, and I also can represent the true force, this impulse by the FH force multiplied by delta T. Okay, now a straightforward implication from this equation is the following. If I now have a smaller collision time interval, if delta T is small, if I move the delta T to this side, if delta T is small, then the FH force will be large, and also of course the true force will be large also. Okay. Because for a collision, there's a known change in momentum. For example, imagine a car colliding with a stationary barrier. Initially, you have a certain momentum, right? mv. And finally, the car after collision is stopped. So the change in momentum is fixed. And that's given by Pf minus Pi. Okay? But if the car has a crumble zone, that means the front part of the car is led to crumble rather slowly. Then there's a longer time of collision. And if you have a longer time of collision according to this equation, the FH force or the true force of collision will be smaller. Okay, so that's why the crumble zone, which lengthens the collision time, will allow you to reduce the collision force. And also, people wear boxing gloves when they play boxing. When you play boxing, you probably don't want to your fist to hurt. You give your other a punch, and you probably don't want the punch to hurt your opponent so much. It's not a sport. It's not a killing. Okay, so people will wear boxing gloves to lengthen the collision time, so as to reduce the collision force. Okay. So that is the basic equation governing the collision time and collision force. Now, in your high school physics, you only learn the F is equal to delta P over delta T. But I now emphasize that the F here is the FH force only. It is not the real force. The real force actually change in a very complicated manner. Okay. Now there are two kinds of collision that is quite important in physics, and they're called elastic and inelastic collision. Now for whatever kind of collision, as long as the body collide and the collision happens in the absence of external force, law of conservation of momentum always hold, as long as there is no external force acting on the body. So whenever you see the collision happening, you can always apply the law of conservation of momentum. Okay. Now, as I say, the collision force is much greater than other forces acting on the system. So you may even neglect the existence of other forces during the collision. For example, if two bodies collide in air, theoretically, there are also gravity force acting on them, right? But during that short moment of collision, the collision force is much greater than the force of gravity. So you can actually neglect the force of gravity at the moment of collision. And you can apply the law of conservation of momentum to the system. As long as you apply it to a moment just before and just after the collision, and everything will hold. The external force can be together. Okay. So that is a powerful law for determine the result of collision, the conservation of linear momentum. Now, there are two kinds of collision. An elastic collision further specify that the total kinetic energy of the system is conserved. But as you know, during collision, some of the kinetic energy may have changed to internal energy. They may change to heat or other form of energy like sound, for example. So, in the real world, kinetic energy must not conserve. But the approximation that kinetic energy is conserved holds in some of the collision. For some of the collision, the kinetic energy loss is small, and we can approximate this collision as elastic collision. So elastic collision is an idealization, which does not really exist in the real world. But let's imagine that for some collision, the kinetic energy change is so small, so we can ignore the loss in energy. And the kinetic energy, total kinetic energy before collision is equal to the total kinetic energy after collision. Okay. And elastic collision has some energy loss. The kinetic energy is not conserved and the energy change to other forms, like for example, internal energy and sound. Now there's a certain situation called complete inelastic collision. Inelastic collision correspond to any collision that has kinetic energy loss. But for complete inelastic collision, the loss in kinetic energy is greatest. And that corresponds to the case when the two bodies, after they collide, they stick together. Okay, when the two bodies collide, they stick together after the collision. That is called an incomplete inelastic collision. And for this case, you have greatest kinetic energy loss among all the other collisions. Okay. Now let's handle the case of a complete inelastic collision. For example, you have a two body M1 and M2. Initially, M2 is at rest, M1 is moving with an initial velocity u. And after collision, M1 and M2 move together, with a velocity V1 and V2 respectively. Okay, so now we consider the first case that the two body merge together after collision, and that is a complete inelastic collision. Now the momentum equation is always whole. It is independent on what kind of collision. For collision, it always whole. Okay, so the initial momentum is M1u, and the final momentum M1v1 plus M2v2. This is the final momentum. The final momentum is sum of the momentum of the individual mass. Okay, now but the body, because we assume that the collision is completely inelastic, so the two velocity after collision is the same. So V1 and V2 is both equal to V. So the equation simplify a lot. If V1 and V2 are both equal to V, then V can be solved. V is equal to M1 over M1 plus M2 multiplied by U. So we can easily solve for the velocity after collision for complete inelastic collision. Now, how about for a elastic collision? Elastic collision is slightly more difficult to handle. The momentum equation still hold, okay? But we also have the conservation of total kinetic energy. The initial kinetic energy is come from the kinetic energy of the first mass, which is half m1u squared. Because we only have the mass m1 moving, the second mass is at rest. The final kinetic energy is a sum of the kinetic energy of the two bodies. Half m1v1 squared plus half m2v2 squared. Okay, so the initial total kinetic energy is equal to the final total kinetic energy. Now we have to solve these two equations for V1 and V2. The equation looks a little bit scary because V1 and V2 in the first equation, they are linear in the first equation. The first equation only contains V1 and V2, but not the square. But for the second equation, you can see V1 squared and V2 squared, and that's a quadratic one. That is to the order 2. That is a quadratic equation. So when you try to eliminate one of the variable, either V1 or V2, you get a quadratic equation, which is which may be look rather scary. Now, but there's a trick to make things more comfortable. Now, this is only a trick. It's not the necessary step. You can use your usual way of solving these two equations. You just can eliminate V1 and V2 from equation 2 using equation 1. But we now want to play with a trick, so it will looks easier to solve this two equation. Now we start with equation 1. We divide equation 1 with m1. So u get rid of m1, v1 also get rid of m1, and the last term become m2 over m1 v2. We move v1 to the left hand side, so it becomes the left hand side become u minus v1. Is that right? Now from equation 2, we can eliminate the factor. We can cancel the factor 1/2, and we do the same thing. We divide by the equation by m1, and so the last term become v2 squared m2 over m1. And after dividing by m1, this two term does not contain m1 anymore, and so I move the v1 square term to the left, and I got u squared minus v1 squared. But by a simple identity, a squared minus b squared is a plus b multiplied by a minus b, right? So I can expand this bracket into u minus v1 multiplied by u plus b1. But u minus v1 is there, right? In this equation, right? U minus v1 is m2 over m1 v2. So I can substitute this guy into here, right? Into this position. And I immediately find that the v2 cancel with one of the v2 on the right hand side. And also I find the m2 over m1, it cancels with the right hand side. So the resulting equation is very simple. After substituting this into here, I get rid of the m2 over m1, and I get rid of one of the v2. So I get a very simple equation of u plus v1. U plus v1 is equal to v2. Okay, so this is a very simple equation. But we now have two equations. The equation 3 and 4 are both linear now. So I can just add up the two equations to eliminate the v1. Okay, we have minus v1 here and plus v1 here. So when we add up the two equations, we got 2u equal to 1 plus m2 over m1 v2. So I can solve for v2. And similarly, I can put the v2 back to this equation, and I can solve for v1. And it happens that after some algebra, I find v1 to be m1 minus m2 divided by m1 plus m2u. So I now got the two v. These are the two velocity, the velocity of the two body after the collision. That is an elastic collision, okay? For elastic case, I got the velocity now. Now, but I want to know, do the equation make sense? I can check whether this equation makes sense when m1 and m2 are of very different mass. Suppose m1 is very large or m2 is very large. I can check for those limiting case to see whether this equation makes sense. Now let us check for the case of m1 much greater than m2. What does that mean? m1 is initially moving, right? So in the initial moving mass is very large compared with the second mass, compared with the mass that is initially stationary. So that means you have initially have a bowling ball. A bowling ball is very heavy, moving with velocity u, colliding with a much lighter ball. And then lighter ball is, for example, a ping pong ball. So now you have a moving bowling ball colliding with a ping pong ball. Okay. Now look at this equation. If m1 is much greater than m2, that means that in the denominator, I can neglect m2 with compared with m1. And also in the numerator and the denominator, I can neglect m2, right? Here, I can neglect m2 with respect to m1. And in the denominator, I can do the same. And so I have m1 divided by m1. And so I got v1 equal to u. But that makes sense. If you have a bowling ball collide with a ping pong ball, then after the collision, the bowling ball will not be affected. Because the mass of the ping ball is so small, it will not affect the motion of the large ball, right? So that means V1 equal to U means the bowling ball still move with the same velocity. It's not affected by the collision at all. But when we look at the motion of the ping pong ball, now in the denominator, we find that M1, M2 is very small compared to M1, so I can neglect this. But now I get 2M1 divided by M1, so I get V2 equal to 2U, okay? So that means the ping pong ball bounce off with twice the initial velocity of the bowling ball, okay? So it bounces off faster at a faster speed, double the initial velocity of the bowling ball, okay? Now, we will come to this again later, but let's believe it, okay? It sounds makes sense. The ping ball must be bounced off with high velocity. But what is y is 2? Y is 2u. We will come to that point later. Okay. Now let's consider another situation. M1 is much more than M2. So that means I initially have a small moving ping pong ball colliding with a stationary bowling ball. Is that right? And in that case, this equation gives what? M1 can be neglected compared with M2. So I've minus M2 over M2, which is become minus U. So that means after the collision, the ping pong ball simply reverse its velocity. The velocity magnitude doesn't change, the speed doesn't change, but the velocity change direction. So it's just like the ping pong ball colliding with a wall. Because the wall is so heavy, the bowling ball is so heavy, the ping pong ball simply bounces back at the same velocity. So the velocity with the same speed, the velocity simply changes direction. Okay, so that is the physics. Okay, and the bowling ball is not affected at all. It's like a mosquito colliding with an elephant. The elephant will not be affected by the mosquito, right? So when the ping ball collide with the bowling ball does not have a change in velocity. Its velocity is still 0, and that can be seen from this equation. If M1 is much smaller than M2, this is essentially 0. Okay. Now this is about 2M1 divided by M2. If M2 is much larger than M1, this is essentially 0. So the bowling ball does not move. So now we check the two limiting case, and they make sense to us, right? Now let's go to the case. Let's examine this case more. Why is when for the first case we have the bowling ball moving initially? Why is the bowling ball bounce off as twice the initial velocity of the bowling? Okay, we examine this case. Now, when we look at this situation from the point of view of an observer who is stationary on the ground, I see this situation: bowling ball moving, colliding with the bowling ball velocity not affected, but the bowling ball move off at twice the velocity of the bowling ball, right? So that is what we observed from the point of view of a stationary observer on the ground. But let us change our point of view. Let us change our point of view to an N who is sitting on the bowling ball. So now I'm in a moving frame, right? I now move together with the bowling ball. Now, so with the bowling ball with respect to this N is becoming at rest because I'm now moving together with the ball, right? And the ping pong ball now appears moving, and it's moving in the opposite direction, right? And so it's initially moving with a velocity minus u. Now, so it becomes the same problem as before. It becomes a problem with a ping ball colliding with a stationary bowling ball. In the frame of reference of this N, I will see the ping pong ball colliding with a stationary bowling ball. And of course, what would happen? The ping pong ball still will bounce off with the same speed. The velocity change direction, right? Now, so how do we go back to this situation? If I look at this phenomenon, not from the point of view of the N, but from the point of view of the person at rest on the ground, I have to add the velocity u to this system. And after adding the velocity u to each of this body, I come up with this situation. This is a change in frame of reference. The two frame of reference, the person at rest on the ground and the person at the ends, and from the point of view of n, they are just different by velocity u. If I add the velocity u to the bowling ball and also the bowling ball, I go back to the frame of reference of the person at rest on the ground. So that explains why the bowling ball has a velocity 2u, because it's just a bowling ball colliding with a stationary bowling ball here. Okay, now this is a change in reference frame. You can understand why this happened by changing the point of view. You change to the point of view of the n, who is sitting on the rest of the bowling ball. Okay, now so let us have a break at this moment. And after the break,